Okay, let's conclude this section on ISO theories with a summary. We started with this figure, which was showing all the interactions that we thought were important, as you remember, and we went through all of them. So let's now summarize. We used basically this model with a planetary boundary layer and a free troposphere with 2 levels, and we argued minimum 2 levels are required because the barotropic component is not always much smaller than baroclinic component. But of course there are many limitations. The cloud radiation damping is basically represented with the Newtonian cooling, and this simple vertical structure doesn't give you the more complicated vertical heating structure that exists in the real MJOs, and the vertical structure of the winds, vertical velocities, and clouds and so on are also not captured. But that was not the idea. As we kept saying, the idea is to understand these processes in as simple and yet as complete a model as possible, and then go back to the real models and see how they do MJOs. I'm not going to go through too many GCMs to show how MJOs are done, but I will show in the next podcast some results from the CMIP6 models, which is the latest crop of IPCC models that are used in the AR6 projections that are just coming out, the AR6 assessment report 6 that is just being released now. So let's summarize the points we have been looking at. At the very heart of interseasonal oscillation model that we looked at are the nonlinear interactions among condensational heating, which is always critical. That's what drives the instability in MJOs. The question is that able to do it by itself or with the waves that it generates? The model is able to generate low frequency equatorial waves. We looked at the Kelvin and Rossby waves. The boundary layer dynamics, which we argued is important, especially because of the frictional convergence and the moisture supply to the free troposphere, which in this case is argued to be the most important feedback, most important non-linear feedback in the ISO theories. Convection, moisture feedback, and wind-induced heat exchanges at the surface. So Vichy and convection moisture feedback, the instability that drives convection, and then the moisture feedback that amplifies the vertical motion, and the heating and so on are also very important. These are nonlinear interactions. These nonlinear interactions result in frictional convergence instability. So you have convection and moisture feedback requiring convergence at the convection moisture feedback and wind-induced heat exchange, requiring convergence at the surface, frictional convergence at the surface, which is a result of these, but then it turns out to be very critical. So looking at the remaining feedbacks from the figure, the model can be extended to include the interaction between the MJO and embedded synoptic systems. So majorly we focused on the MJO and included mesos as a way to explain the northward propagation of the Rossby waves because of the background flow. So there was an inclusion of the background mean state or seasonal circulation already to explain the boreal summer interseasonal oscillations. The impacts of three-dimensional background circulation, of course, as well as the effect of interactive SST feedback. So the simple mix layer, which is also a model limitation, but we showed that it does have strong cloud SST feedback and wind SST feedback. Again, these are represented in a simple way, and in the real world they are more complicated and one has to see whether the GCMs do it better compared to the observations, or what can be understood from nature. The four feedback processes that we considered again were the convection wave convergence feedback, frictional moisture convergence feedback, evaporation wind feedback. So this is the Vichy where the critical aspect was that the background winds are considered easterly, so the surface winds associated with the MJO convection wave convergence feedback was that the associated anomalies at MJO timescale are easterly, so ahead of the convection there is increase in the wind speed, increase in the background wind speed because of the contribution from the MJO winds, which increases the latent heat loss. And behind, I hope I have it right, behind you have westerlies, where the westerly winds associated with the MJOs were able to change the latent heat flux as well. So we had shallowing of the mixed layer and warm SSTs ahead, and deepening of the mixed layer and cold SSTs behind, that we had seen in this kind of figure. So you saw warming and cooling and shallowing of the mixed layer and deepening of the mixed layer. That was also important for the feedback. So considering the moisture feedback as well, frictional convergence feedback is emphasized in this particular model because global circulation that is coupled to a large scale complex of convective cells can be better explained by the frictional convergence. Baroclinic structure with the winds converging in the boundary layer in front of the main precipitation. So there is a scale selection of the Kelvin waves and the Rossby waves. Kelvin waves preferring the eastward propagation, and the Rossby waves and the frictional convergence associated with them help in slowing down the eastward propagation. So the explaining the convectively coupled Kelvin waves and the proper feedback propagation speed is possible with the frictional convergence. The other feedbacks give you reduced stability, but the reduction in speed is not fully explained. Okay, so that's important. So that's horizontal circulation consisting of both equatorial Kelvin and Rossby waves, and the slow eastward speed that is observed about 5 to 10 meter per second, should be -1 there. Sorry, let me put the laser again, I keep forgetting. Okay, so movement that gives rise to the intraseasonal time scale is better explained by the frictional convergence. The multi-scale structure of the convective complex involving eastward propagating supercloud clusters with the backward tilt, and ahead of the MJO pocket we had westward propagating two-day waves which had a forward tilt, and this multi-scale interaction was better explained by the frictional convergence feedback as well. Longitudinal variation and seasonal variation in the activity center and propagation, especially the prominent northward propagation and off-equatorial westward propagation of the disturbances in the Asian monsoon region during boreal summer, could be captured by this, given the seasonal background winds. Remember the easterly shear, for example. And finally, SST anomalies lead, and the strongest surface heat exchange lags behind a major convective complex. Oops, I missed a word there, but you get the idea. So I think it's clear why this model is built to focus on the frictional convergence as the most important feedback, because the author truly believes that's the case. And as I said multiple times, not every model believes in the same thing. So this model claims to explain most of the features, which again has to be explained in the full models, because this is not a full model, this is a process model, and it does help explain a lot of the things. But all the simplifications that we talked about are definitely something to remember. I will leave it here and then conclude this series of lectures with a very brief look at the CMIP6 models, but also touch on how the GCMs with their convective parameterization have a sensitivity to convective parameterization in terms of all these feedbacks, and how that affects the MJOs in the GCMs. We will just look at one example of 10 to 20 day and 30 to 60 day propagation speeds in a model with different convective parameterizations. So that is now being looked at also with the NICAM model, which has no explicit no parameterization and explicitly does convection, run at very high resolution, and it is argued to produce many of the features realistically, but it's such a high resolution model that it only could be integrated for a very short time. So there are limitations on how to do that, and then there are parameterizations produced for those important processes to go into lower resolution models, and there is an argument that they improve the MJO and ISO properties in terms of amplitude, propagation, vertical structure, and so on and so forth. So still many open questions, but also many open science problems to work on, right?